Hello everyone. In this lecture I shall discuss the numerical solution of system of linear equations. Basically I will give a brief introduction about the numerical methods, and I will discuss the first two preliminary methods, Gauss elimination method and Gauss-Jordan elimination method. For details of these preliminary things, you may recall or refer to my lecture series on linear algebra. A first few lectures you should see it, where the details of the direct methods and the existence criterion are discussed. Okay, so for a system of equation, I discuss here for a 3x3 system for simplicity. However, it can be extended to m cross n system. Okay, and few methods are also restricted to square matrix. Number of equations and number of variables are same, m equal to n, right? So now if you consider a system of equations with three unknowns and three equations, a11 x1 plus a12 x2 plus a13 x3 is equal to b1, and a21 x1 plus a22 x2 plus a23 x3 is equal to b2, likewise this. So now in matrix form we write this. These are the coefficients. We separate the coefficients. These are the coefficients. We separate the coefficient a. We separate the variable x1, x2, x3, and we separate the right hand side constants b1, b2, b3, and we write in matrix form ax is equal to b. We write in matrix form ax is equal to b. It is a linear system of equation where a is the coefficient matrix. A is the coefficient matrix, x is your unknown vector, x is your unknown vector, and b is the constant vector. B is the constant vector. Now this A together with this B, right, because any changes in the left hand side should be accompanied with the change in right hand side. So this A and B together is known as the augmented matrix. Okay, A together with the B, just press a gentle line and separate them, so that whatever the operation performed in the left hand side, the same operation will be performed in the right hand side to get the solution of the system. Okay, so now there are some direct methods as well as the iterative methods, where direct method will not work. Moreover, for a large systems the iterative method will work. Okay, for the details, before the details of this discussion, let me to introduce myself. Myself, Professor Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, in short Visut Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the details of the methods for the solution of the system of equation. Now, as I have told you, this is A together with B is equal to the augmented matrix. Now to solve a system of equation Ax is equal to B, we have our direct methods such as your Cramer's rule, matrix inversion. These are already known in your 12th standards. And now your Gauss elimination method and Gauss-Jordan elimination methods, the details of these methods we have discussed in our linear algebra lecture series. You should refer to the first few lectures. Here also I will discuss a brief idea on these with a example, so that this will help you for the further analysis. Now this Gauss elimination method and Gauss-Jordan elimination method, these are based on elementary row operation technique. Okay, these are based on elementary row transformation or elementary row operation technique, and these are all direct methods. Moreover, this LU decomposition method, is preferred over these methods because this is quite friendly for computation or to design a software. Okay, it is better for computational aspect, right? Computational aspects, and it is better. Okay, and we will discuss the details of the LU decomposition here, or it is also known as the triangularization method or matrix factorization method. And your iterative methods, where the direct method will not work, or for a large system we use the Gauss-Jacobi method and Gauss-Seidel iteration method. Gauss-Seidel iteration method is more dynamic, and these methods are basically used for large system. Okay, large systems. If m and n are large enough, then we should use this. And moreover, where this method fail also, direct method fails, we use iterative method. And also if for large system we use the iterative methods. Okay, so now let us first discuss the direct methods. In view of that, I will discuss here the Gauss elimination method and Gauss-Jordan elimination method, which are based on the elementary row transformation. So what is your elementary row transformation? Suppose you are given a system, suppose x plus 2y plus 3z is equal to 5, 3x minus y plus z is equal to 3, x minus y plus 7z is equal to 8, say. Okay, so now this is a system. You are asked to solve this system. This is if I interchange any two row, if I write this, if I bring this row here and this row here, then no issue. Means the elementary row transformation is, the first one is you may interchange any two row, right? Interchange any two row, it will not affect the system. I can write it Ri is replaced by Rj, right? Or I can interchange Ri and Rj. And coming to the second, if I multiply a constant, non-zero constant, suppose to both sides of this, suppose I multiply 5 to both sides, then the left hand side and right hand side is balanced. Means a row can be replaced by a constant multiple of the same row, right? But that constant should be a non-zero constant, right? Any row can be replaced by a non-zero constant multiple of that row. And third, suppose if I add this two row with certain constant multiplication to create a third row, and I replace one row, then also the system is not going to change. Means we can increase the row by a constant multiple of another row, we can also decrease also, right? We can increase or decrease a row. This is the most important property. And in view of this property also, we can have a multiplication here, right? Then the system is not going to be changed here, right? And this k1, k2 should be the non-zero constants, right? So these are the three elementary row operations, and the Gauss elimination and Jordan elimination are based on these three elementary row operations. So now coming to the these two methods. Now coming to the working rule of these two methods, Gauss elimination method and Gauss-Jordan elimination method. We consider the augmented matrix, right? We consider the augmented matrix AB, right? Then we transform this to a upper triangular matrix. Okay, transform this, reduce to a upper triangular matrix. How we will reduce it? By using elementary row operation, right? So then by back substitution method, find the solution, okay? So here in Gauss-Jordan method, what you will do? Consider the augmented matrix, right? Augmented matrix AB. So now reduce it to a diagonal matrix. And the diagonal elements are unity, and preferably to an identity matrix, say. Then directly you solve, right? Here we use back substitution in Gauss elimination, but directly you solve now, okay? Directly solve. So this method, and here it is less time consuming, but here, right, more steps are needed. More steps are needed here, right? So it is lengthy. So it is lengthy here. It is lengthy here, right? So this Gauss elimination method is preferred. Gauss elimination method is preferred here. That means what we are doing? That means here you are given a matrix here. You are given a matrix here A11, A12, A13, A21, A22, A23, A31, A32, A33, and you gently press a line. You write the right hand side B1, B2, B3. So whatever the operation is performed, it is in left hand side as well as in right hand side. At the first step, what you will do means your intention is to bring it to a triangular matrix. Upper triangular matrix means below this diagonal, this element should be zeros. Okay, so at first step you use this to bring this element as 0. You bring this 0 and bring this 0. It is your step 1. It is your step 1. And in step 2, what you will do? In step 2, you use this to bring this position 0. It is your step 2. Okay, so now this system is reduced to A11, A12, A13, some B1 here, and it is becomes here 0, and there will be a certain change here. Okay, A23 dash and B2 dash, there will be some change here, and again here it is 0, and it is again there will be certain change, A23 star and suppose B3 star, there will be a certain change here. Okay, so now by using the back substitution method you can solve it. Back substitution method means your A23 star Z is equal to B3 star. Accordingly you find Z, right? You use back substitution method. Back substitution method here you use. Okay, then coming to this row means here A22 dash Y plus A23 dash Z is equal to B2 dash. So you substitute Z here. So this implies you get the value of Y. Then coming to your row 1, here A11 X plus A12 Y plus A13 Z is equal to B1. You substitute the value of Y and Z. Okay, substitute the value of Y and Z to find the value of X. So this is what the Gauss elimination method. But in Gauss-Jordan elimination method, what we are doing? You consider the matrix A11, A12, A13, A21, A22, A23, A31, A32, A33, and the right hand side is here B1, B2, B3. So what you are doing here, you consider the augmented matrix. In each case we are considering the augmented matrix. Okay, A together with B we are considering. So after that, at step 1, what we are doing? The same as in Gauss elimination method. Use this to bring this position 0 and bring this position 0. Right, at step 1 you adopt this. Then coming to a step 2, right, in Gauss elimination method you are performing this. So at the same time here you have to perform this also. This is your second step. And in third step, right, you have to adopt this. Use this to bring this position 0 and this bring this position 0 here. Okay, so accordingly the reduced system will, this is your third step. So the reduced system will be, so it will be say A11 star 0 0, 0 A22 star 0 and 0 0 A33 star, it will be there. And here also there will be certain change here, B1 star, B2 star and B3 star. There will be certain change here. It is here actually a diagonal matrix here. It is again a diagonal matrix. But if you want to bring it to your identity matrix, then also we will able to 1 0 0, 0 1 0, 0 0 1. Then here B1 star, B2 star and B3 star. Okay, in that way you reduce to a identity matrix. After that you find the value. This is your X is equal to B1 star and your Y is equal to your B2 star and Z is equal to your B3 star. So here we get it directly. But here we have to solve it this back substitution method. This is the difference. But here this is time consuming here. So here this is time consuming. You calculate these operations, extra operations you calculate here. So this is time consuming here. So out of these two methods, this Gauss elimination is preferred, okay, over this Gauss-Jordan eliminations. So let us solve one problem to see the difference of these two methods. So now recalling the existence of the solution, if we are getting rank A is equal to rank AB, right, rank AB, and here rank of A is equal to rank of AB, right, rank of AB. In this case the solution is consistent, and here it is equal to number of unknowns, and it is, suppose here it is less than number of unknowns. So in this case it will lead to, if it is number of unknowns, it will lead to unique solution. If it is less than number of unknowns, then it leads to infinite solution. In both the cases here, rank A is equal to rank AB. If this will happen, then the solution exists, right? And in this case we say the system is consistent. In both the cases we say the system is consistent, right? Means the solution exists here. Now if in the third case, if here rank A is not equal to rank AB, okay, rank AB, then in this case we have no solution. No solution means the system here is inconsistent, okay, here it is inconsistent. In particular, if I give you one example, suppose you have a reduced system is like this: 2 3 5 4 0 2 0 0 2 say 0 2 3 6 say 0 0 5 7. So suppose after the reduction we get it like this. What we are getting? So here we are getting, this is my A, and this together total is my AB, right? So what we are getting? Rank A is here 3, and from this perspective of AB it is also 3, right? And the number of unknown is 3. So here it is a unique solution case. It will lead you to, means it will give you 5z is equal to 7, right? It leads to your unique solution. So similarly, if you have your 2 3 5 4 0 2 3 6 0 0 0 0, we are getting, you see here the rank of A is same thing as rank of A is 2 here, and if you think from this perspective also, it is also 2 here, but it is less than the number of unknown is 3, right? So rank A is here rank AB, but it is less than n number of unknowns. So here it is infinite solution, because last row is 0 equal to 0 is valid, right? So one row is less to find 3 variables, right? So now in both the cases here, and it is consistent, means the solution exists. In both the cases it is consistent. Now coming to another example, suppose we are getting 2 3 5 4 0 2 3 6 0 0 0 5. So you see here this last row gives you 0 is equal to 5, which is not possible, right? And here rank A is what? Rank A is 2 here, but rank AB is what? Rank AB is 3. Rank A is not equal to rank AB, right? So here it is no solution, and the system is inconsistent here, okay? So now come to one particular example to solve both the cases. So suppose you are given one example, solve a system of equations, 3 equations, 3 variables by Gauss-Jordan elimination and Gauss elimination and Gauss-Jordan elimination. Right, now coming to Gauss elimination method. Gauss elimination method. You consider the augmented matrix. Consider your augmented matrix AB is equal to, just to collect the coefficient, 1 2 7 2 3 1 3 4 1. Okay, you see this you ensure here A11 should not equal to 0, otherwise you interchange, else interchange to get A11 is not equal to 0. This caution should be there. Okay, this caution should be there. So now your first step is use this to bring this position 0 here. So how you will achieve this? Means R1 remains silent, your row 2 will be replaced. If I multiply a 3 in row 1, and one more thing, you just gently press a line and write the right hand side also. The right hand side is your 4 5 7. Okay, so at the first step your row 2 is replaced by row 2. If I multiply 2 in row 1 and subtract, then this place becomes 0, this place becomes 0. Then coming to your third row, row 3 is replaced by row 3 minus 3 row 1. Okay, so after that your row 1 remains silent, 1 2 7 4, no change in row 1, and here obviously it will 0, and here obviously it will 0. This was our intention. Accordingly the some changes here and here. Okay, we note the changes. So R2 minus 2 R1, it is 3 minus 4, right? It is 3 minus 4 is your minus, just one second. Actually in the question it is 3. Okay, in the question it is 3. So what are the changes you need? So your R1 is replaced, you multiply this coefficient here and this coefficient here, so that if you multiply 3 over here it will 6, if you multiply 2 over here it will 6. So it is R2 is replaced by 3 R2 minus 2 row 1, and R3 is replaced by simply R3 minus R1. Okay, simply here R3 minus R1. After that your calculation will be 3 R2 minus 2 R1, it is 9 minus 4 is your 5, and here similarly you compute it, it is minus 11, it is 7, and it is 2 minus 6, and it is at 3. Okay, so in the next step what you have to do, you use this to bring this position 0. So in next step you perform R3 is replaced by, you just multiply this with this, 5 R3, and you multiply 2 with this. Okay, so minus 2 times R2. Now here you see here row 1 remains silent, row 1 is 3 here, row 1 is silent here 3, it is 2 7 4, row 2 remains silent, 0 5 minus 11 7. Okay, and now there will be change here, this is automatically 0. Now you calculate it, 5 into row 3 minus 30 plus 22. Okay, so this will be your minus 8, and this will be your 1, this will be 1, it is 15 minus 14 is 1. So now we are at the reduced system. Okay, now it is you see here, now it is a upper triangular matrix, is not it? So now come to the back substitution. Coming to the back substitution method. Back substitution method we are using. From the last row we have minus 8x3 is equal to here 1. We have taken x1, x2, x3. Yes, 8x3 is equal to 1. From the second row we have here 5x2, 0x1 plus 5x2 here 5x2 minus 11x3 is equal to 7, and from the first row 3x1 plus 2x2 plus 7x3 is equal to here 4. So solving the first this last row we are getting x3 is equal to minus 1 by 8. we substitute this x3 here, and you solve for your x2, right? So this x2 will be your 45, it will be your 7 minus 11 by 8, it will be your 45 by 40, right? So this will be 9 by 8, so this will be 9 by 8. Now coming to your z, right, you substitute the value of x3 here, substitute the value of x2 here, so this implies here x1 will be your 7 by 8, right? So this is x1, this is x2, and this is x3, right? So this is the solution. Therefore your x1 is 7 by 8, x2 is 9 by 8, and x3 is minus 1 by 8. So this is the desired solution, and this solution is unique here. Okay, now let us solve the same problem by Gauss-Jordan elimination. So coming to the Gauss-Jordan elimination, okay, method. So by this Gauss-Jordan elimination method, we consider your augmented matrix, same thing, it is your 3 2 7 4 2 3 1 5 3 4 1 7. Okay, so the same first step is same here, because you use this to bring this position 0 and bring this position 0. So the first step is same here. So you adopt the same operation here. R2 is replaced by 3R2 minus 2R1, and R3 is replaced by R3 minus R1. Okay, so here the first row remains silent, 3 2 7, it is 4, and second row it becomes here 0, it becomes here 0 0, and the calculation here is 5 minus 11, and it is 7, it is 2 minus 6 and 3. Okay, now in the second step what you have to do, you have to bring this 0, and at the same time we have to bring this 0. Okay, so what will be your operation? So your operation will be, you see in this numerator here, right, if you multiply 5 R3, you multiply 5 here, you multiply 2 here, avoid fraction. Okay, so here R1 is replaced by 5 R1 minus 2 R2, and here R3 is replaced by, right, here 5 R2 minus R3 minus 2 R2. However, the other operations, alternatively, if you adopt simply R1 is replaced by here R1 minus R3, then also it is okay, right, any operation, but to have a pattern we should use it. To have a pattern we should use it. Okay, to have a pattern we should use it. However, we can also use it any operation, right, because row operation. So now with this, adopting this and this, we have the calculation here is the middle row remains silent, 0 5 minus 11 7, and here the first row becomes here 5 R1 means it becomes here 15, and accordingly here it is 0, and here it is becomes here 57, it is here 6, it is here 0 0 minus 8 1. This operation is same as the operation below this diagonal is same as this, is not it? It's same as this. So your downward operation coincides with your previous. Okay, now coming to the last step, we have to use this to bring this position 0. You need to bring this 0 and bring this 0, for which you have your operation here is, your R1 is replaced by, right, here 8 times R1, and since it is in opposite sign, plus 57 times here R3, and your R2 is replaced by same sign, so it is negative, my 8 times R2 plus 11 times R3, and your last row remains silent, 0 0 minus 8, and it is 1. So after these operations we get it 128 is multiplied, 15 into 8, it will be here 120, and it is here 0, and it is here 0, and it is here 0 40 and 0. In the right hand side it is 105 and here it is 45. Okay, so now we compute, rather than bringing 1 and 1 we compute it here. So it is 120x. So this implies 120x is 105, implies x is x1 is here 105 by 120. Okay, so this is your 7 by 8. Then coming to your x, this will give you x2, 40 x2 is equal to your 45, implies x2 is 45 by 40. Okay, it is 9 by 8. Then coming to your x3, here minus 8x3 is equal to 1. So your x3 is equal to your minus 1 by 8. So you see, is it not coincide with this previous? So x1 7 by 8, 9 by 8 and minus 1 by 8. So therefore here x1 is 7 by 8, x2 is 9 by 8 and x3 is minus 1 by 8. So this is your answer. Okay, so this is your answer. So you see, so here though we get the answer directly here, so directly we are getting, but here this computation is lengthy here, is not it? But this computation is lengthy here, right? So we should prefer the Gauss elimination method. So to conclude, in view of solving a system of equation, we have our direct methods, we have our indirect methods. Indirect methods are basically the iterative methods, and direct methods as I have mentioned, and this Gauss elimination method and Gauss-Jordan elimination method. Gauss-Jordan is somehow direct but it is lengthy, and Gauss elimination methods needs your back substitution technique. Okay, so in the upcoming lecture I shall discuss the most important direct method is LU decomposition method, LU factorization method. Okay, and of course the Gauss elimination method is used in computer programming, but it is preferred, right, to design the software. This algorithm based on your LU factorization method is most important. Okay, so we should discuss it in our subsequent lecture. So now my appeal to all of you, if you feel that this lecture is useful and interesting for you, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures. At the same time, the lecture what is being uploaded will come to your screen and you will find the lecture immediately. So let us close the lecture. Thank you all. Have a nice day.